Hello everyone, welcome back. In this video, we are going to learn another important concept in Java multithreading, and that is deadlock. So we will see with a clear explanation and practical examples. Subscribe to the channel to keep learning and growing your Java skills. Now let's get started. So imagine running a Java program that compiles successfully. Okay, so there is no compilation error, no exception, no infinite loop, and suddenly your application stops making progress. Okay, so let's say thread 1 is waiting for thread 2 and thread 2 is waiting for thread 1. So 1 is waiting for 2 and 2 is waiting for 1. So in such cases, neither of these threads can continue and the program may remain stuck forever. So both threads are stuck forever. Okay, so this is the one of the most dangerous problems in multi-threaded programming that we call as deadlock. So in this video, we will actually create a deadlock in Java, understand exactly why it happens, and then fix in the same code using one simple but extremely important technique. And at the end, I will show you the locking rule that can prevent many deadlocks before they happen. So before happening only, we will resolve the deadlock. Okay. So what is deadlock? So a deadlock occurs when two or more threads become permanently blocked. So as we have seen in the example, like thread 1 was waiting for thread 2 to finish and thread 2 was waiting to finish for the thread 1. So they are waiting for each other and they are in deadlock. So it can occur when two or more threads become permanently blocked. Why? Because each thread is waiting for a resource held by another thread. Okay, so let's say T1 is using one resource. Okay, T1 is using some resource R1 and T2 is using resource R2. Okay, now T2 wants to use the resource R1, but currently that is captured by T1. Okay, so T2 will wait until T1 finishes. And likewise, thread 1, T1 is waiting to use the resource for R2, which is currently held by thread 2. So both are waiting for each other and they are in deadlock. Okay, so they are waiting for resource held by another thread in the cycle. So you imagine like thread 1 owns lock. Okay, lock A, and it needs lock B. Okay, so thread 1 currently it is acquiring lock A, but it is waiting for getting lock B. Okay, and at the same time thread 2 is holding lock B, but it is waiting for lock A. Why it is waiting for lock A? Because it wants to use the lock A. So in such case, no thread can proceed, no thread can continue, and neither can reach the point where it releases the lock. Okay, so they are in deadlock state. Now, so the easiest way to visualize what is deadlock or deadlock as a cycle, thread 1 holds lock A, okay, and it wants for lock B. Okay, and thread 2 holds lock B, but it wants lock A. But currently lock A is held by thread 1. So this creates a what? Circular dependency. Circular dependency. So thread 1 is acquiring lock A and thread 2 acquiring lock B. But thread 2 needs lock A and thread 1 needs lock B. So both are in circular dependency. So for either thread to continue, the other thread must release a lock. If any of the thread is releasing lock, then other thread can utilize it. But both are waiting for each other lock and both are holding the same lock. Okay, so this circular waiting pattern is one of the key signs of a deadlock. Okay, now we will see one example of deadlock. So here we have one example. So we have two lock objects. So these are what? These are lock objects. Okay, we have created lock 1 and lock 2. So these are two objects, lock 1 and lock 2. Okay, now there are two threads, thread 1 and thread 2. So we have two locks and we have two threads. So thread 1 will first acquire lock 1, okay, and then lock 2. So after acquiring lock 1, it will try to acquire lock 2. Okay, and similarly, thread 2 will do opposite. How? Thread 2 will acquire lock 2, and after acquiring lock 2, it tries to acquire lock 1. Okay, so look carefully at the order. Thread 1 goes lock 1, goes from lock 1 to lock 2, and thread 2 goes from lock 2 to lock 1. So that opposite lock ordering is what creates the possibility of deadlock. Okay, so in order to resolve this issue, how can we resolve this issue? Because both are in opposite in nature. Okay, so let's see. So how the deadlock happening? So we will see step by step. So first step, what it is doing? Thread 1 is acquiring lock 1, and after that thread 2 is acquiring lock 2. Okay, so lock 1 and lock 2 are acquired at the moment. Okay, now at the third step, thread 1 wants to acquire lock 2, but lock 2 is currently acquired by which thread? Thread 2. So thread 1 will keep on waiting until thread 2 releases the lock 2. And likewise, thread 2 wants lock 1, which is acquired by thread 1. Okay, so thread 2 is waiting for thread 1 and thread 1 is waiting for thread 2. Okay, so thread 1 cannot continue until thread 2 releases lock 2, and thread 2 cannot continue until thread 1 releases lock 1. Neither of them can continue. That is deadlock. This is the example of deadlock. Okay, now can you predict what will happen in this case? So let's say thread 1 owns lock A. Thread 1 is owning what? Lock A. And thread 2 is owning lock B. After the short delay, thread 1 tries to acquire lock B. See, sleep is there, right? So after some time or delay, it is trying to acquire lock B. And thread 2, after some time, it is trying to acquire lock A. So which thread finishes first? Thread 1 finishes first, thread 2 finishes first, or both may wait indefinitely. So what is the answer for this one? So the answer is this one. Both may wait indefinitely. Why? Because it is circular dependency. Thread 1 is owning lock A. Thread 1 is owning lock A, and it is trying to acquire lock B. So lock B is currently acquired by thread 2. So thread 1 cannot acquire lock B until thread 2 releases lock B. And vice versa. Thread 2 is owning lock B and waiting for trying to acquire lock A, which is lock A is currently acquired by lock A, thread 1. So thread 1 will release lock A, then only thread 2 can acquire lock A. So they are waiting for each other, and both threads may wait indefinitely. Okay, so the threads can simply remain blocked. That is one reason deadlocks can be difficult to diagnose, also to identify. Okay, then you might wonder, why does not Java simply release one of the locks automatically so that both threads can coordinate with each other? If one is releasing lock, then another can utilize, right? So the problem is that synchronized locks are normally released when it is released when execution exits. So let's say we have some synchronized block. So this is synchronized block. Okay. So when the lock is released at the end of the synchronized block, lock will be released. Okay. Released automatically by Java. So that is like automatically released by Java. But what we are doing? So thread 1 cannot reach at the end of synchronized block. Why? Because in between of this code only thread 1 is waiting for thread 2 to finish. So it is never reaching the end of the block. In between the synchronized code, it is thread 1 is waiting for thread 2, and likewise we have another synchronized block in which thread 2 is waiting for thread 1 to finish, and it is never reaching the end of the block. That's why lock is not released automatically by Java. So automatically releasing locks at arbitrary points means in between the curly braces, in between this synchronized code, could also violate the correctness of the protected operation. Okay, so both threads will be remain stuck. So what is the correct solution then? So the correct solution is to design our locking strategy so this circular dependency could not occur. Okay, now how to prevent this kind of deadlock? How do we fix it? So one of the most effective ways to prevent this type of deadlock is consistent lock ordering. What is consistent lock ordering? So previously thread 1 acquired lock A, then lock B, correct? And thread 2 acquired lock B, then lock A, reverse, opposite order. So this was creating what? Circular dependency, correct? Circular dependency. So instead we created one rule. So whenever both locks are acquired, every thread must acquire them in the same order. It should not be in the opposite order. If you see here, order is opposite. Lock A is acquired by thread 1, then it is trying to acquire lock B. And likewise, thread 2 is acquired lock B and it is trying to acquire lock A. So these are opposite in nature. So it should be same order. So if thread 1 is acquiring lock A first, then lock B. So similarly, lock 2 should also acquire lock A first, then lock B. Okay. So that's how we can approach the consistent lock ordering. Okay. So always acquire locks in the same order. Okay. So here is the example. Thread 1 is acquiring lock 1 first, then lock 2. Okay, see, this I was explaining. It is never reaching the end of the curly braces, end of the synchronized block. Why? Because in between this, we are waiting for another thread to finish lock 2. Okay, that's why it was not automatically closed by Java, released by Java. So what we are doing, the order should be same. So lock 1, then lock 2. Similarly for thread 2. Okay, so now both threads acquire the locks in exactly the same order. Lock 1 first, then lock 2. Okay. Now suppose thread 1 acquires lock 1, thread 2 cannot acquire lock 1 at the same time. Okay, so we are saying like it should be in same order, right? We are saying the lock should be in the same order. So I am saying, okay, T1 is acquired lock 1, okay, and let's say thread 2 is also trying to acquire lock 1, okay, but thread 2 cannot acquire lock 1 at the same time, so it will wait some time before acquiring any of these locks. Okay, so thread 1 can acquire lock 2, complete its works and release both locks. Okay, so after that thread 2 can proceed. So what I am saying is thread 1 will acquire lock 1, then lock 2, and once it is finished, thread 2 can acquire lock 1 and lock 2, like this. So the circular waiting pattern has been removed. Okay, so this demonstrates one of the most important deadlock prevention rule, that is when multiple locks are required. In this example, we are taking example of two locks, lock 1 and lock 2. So when multiple locks are required, use a consistent global lock ordering. What I'm saying? Consistent lock ordering. Consistent lock ordering is what? It should be in the same order. So here we have seen in the example lock 1, lock 2. Here also lock 1, lock 2 for both the threads. Okay. Now we will see nested locking. So another useful strategy is to avoid unnecessary nested locking. So the more locks, okay, here you can see 3 locks. So the more locks a thread holds, okay, while trying to acquire additional locks, the more complex the dependencies between threads become. It will be more complex. Complex lock dependencies will make deadlocks harder to find out, diagnose. Okay, so this does not mean like nested locks are always wrong. Sometimes they are necessary based on our requirement. But when possible, simplify the locking design and avoid holding multiple locks at the same time unnecessarily. So based on our requirement, only if it is necessary, then only we should go for this applying multiple locks. Okay. Now, another good practice is to keep lock scope as focused as possible. What do we mean by focused? So if a thread holds a lock while performing long running or unrelated operations, okay, so long operation or unrelated operations, okay, a lock is holding for a longer duration, and other threads will, what they will do, they will keep on waiting for longer time, other threads. So this will increase what? Lock contention, and can make locking problems harder to manage those things. Okay, so be especially careful about performing operations with unpredictable duration, okay, while holding locks. So such a certain input output IO, okay, external calls, operations to external code, protect the shared state. Okay, protect the shared state means what? Synchronized code, because it requires synchronization, because one thread is utilizing and other threads are waiting. Okay, and design, we should design critical section very carefully. Okay, now we will see one prevention, how to use that one. So Java also provides explicit lock APIs, okay, such as re-entrant lock. Okay, so re-entrant lock provides methods. So re-entrant lock provides a method such as try lock. Try lock is the method name. So with try lock, a thread can attempt to acquire a lock instead of necessarily waiting indefinitely. That means, so one thread is acquiring lock, okay, and there are, let's say, multiple other threads are there which are waiting to acquire the lock. So once it is released, these threads will get a chance to acquire the lock. Okay, so with try lock method, what will happen? These threads can attempt to acquire a lock, okay, instead of necessarily waiting indefinitely. So there is also a timed version, okay, timed version. So the application can back off or release other locks if appropriate. You can think like it will retry or take another actions. Okay, so this can be useful when designing more advanced deadlock or avoidance strategies. Okay, so it is written here, can avoid waiting forever for a lock. So whenever we successfully acquire a re-entrant lock, we should normally release it in a finally block. Here you can see in a finally block we are releasing the lock to ensure that it is unlocked properly. Okay, now let's summarize some practical strategies for reducing deadlock risk. So first of all, establish consistent lock ordering. We have seen in the example consistent lock ordering, so it should follow a consistent order for every threads. Okay, so if multiple threads needs multiple locks, acquire them in a consistent order. The ordering should be same. Okay, so consistent lock ordering. And second is avoid unnecessary nested lock. Okay, and third is keep critical section focused and avoid holding locks longer than necessary. Okay, and fourth one is consider try lock method of re-entrant. Okay, so for suitable designs consider explicit lock API. Okay, so try lock to gain more control. It will provide some more control over lock acquisition. Okay, and finally understand your lock dependencies. Okay, so which lock does each thread currently hold? Which lock is it trying to acquire next? If those dependencies can form a cycle, you may have a deadlock risk. So always ask these questions before implementing these locks. Okay, now so there are 4 classic conditions associated with deadlock. First is the mutual exclusion. Mutual exclusion, that means a resource can be exclusively held by one thread at a time. Okay, so we have like one resource, so this resource can be utilized by one thread at a time, and other threads will keep on waiting until this thread releases this resource. And second is hold and wait. So a thread holds one resource while waiting for another. And third is no preemption. Okay, so the resource is not simply taken away from the thread holding it. And the fourth is circular wait. We have seen in the example circular wait. So cycle exists where threads are waiting for resources held by each other. We have seen in the example, right? So there were 2 threads and both are waiting for each other resources. So this was circular waiting, circular dependency. So if we design our system, so at least one required condition cannot hold, so we can prevent deadlock. So for example, consistent lock ordering, we have seen, right? Consistent lock ordering, that means order should be same. So consistent lock ordering is designed to eliminate this kind of circular wait. Okay, now yeah, here is the simplest model for deadlock. So thread 1 owns A and wants for B, and likewise thread 2 is owning B but it is trying to get A, waiting for A. So that creates a cycle. Neither can make progress. To prevent this specific pattern, break the possibility of the cycle. So it is like circular wait, right? It will lead to the deadlock. So one powerful technique is to define a consistent lock order. So if every thread acquires A before B, the circular dependency cannot form. Okay, cannot form between these 2 threads, 2 locks in this way. So when you see multiple locks, always ask in what order are these locks being acquired. Okay, now Yeah, so we have now seen how deadlock can cause threads to wait indefinitely and how careful lock ordering can prevent many deadlock scenarios. Okay, but here's something interesting. A program can fail to make useful progress even when there is no deadlock. So, one thread might continuously lose access to the resource it needs and barely get a chance to execute for that resource. So that problem we call it as starvation. So it is written here, one thread never get enough CPU or access to resource. We call it as starvation. Or there is another condition in which two threads might remain completely active, constantly responding to each other, but still never able to utilize one, accomplish their task. Okay, so threads keep reacting to each other, but no useful progress happen. We call it as live lock. So these are like deadlock, starvation, live lock may look similar kind of situations, but they happen for very different reasons. And understanding those differences is the next step in mastering Java concurrency. Okay. So that's all for this video. I hope you now have a clear understanding of deadlock in Java. Thanks for watching and I will see you in the next video.